We're looking at indeterminate forms and L'Hopital's rule. 7.7 is so ridiculously helpful for us in getting ready for the AP exam because it's going to give us a much easier way to do some of our limits that we have done before. It will give us a way to do some limits that we could not do before. So here's what we're talking about when we refer to an indeterminate form. Let's say that we have the limit as x approaches 1 of ln x over x minus 1. All right, so if I plug 1 into each of those, I'm going to have ln 1 over 1 minus 1. So that's going to give me 0 over 0. Okay, what's 0 divided by 0? Since division by 0 is undefined, does that mean my limit doesn't exist? Well, it definitely means it's not well behaved, but that doesn't mean it necessarily doesn't exist. Those were the types of problems where we would try to rewrite what we were taking the limit of if it wasn't well behaved and make it well behaved. So maybe we would factor and cancel, or we would rationalize, or try and find some way, anything in our algebra toolbox that we had ever learned in all of our life as a way to rewrite that to make it well behaved. This is going to give us another tool to help us with that. Here's another indeterminate form. Let's say that we had the limit as x approaches infinity of ln x over x minus 1. So that same equation, only this time we're approaching infinity. All right? If you think about the numerator, if you have the natural log of x, where x is a value that is getting infinitely larger without bound. All right? Now, when I write ln infinity, I'm putting infinity in the place of x there. When I'm writing ln infinity, we've talked about this before, earlier in the year when we were talking about limits. I'm not referring to infinity as a number. We all know that infinity is a symbol that represents the concept of something getting infinitely larger without bound. But when I'm doing line by line by line by line of work, I don't want to sit here and say, if I take the natural log of something getting infinitely larger without bound, I don't have time for that. I need a succinct way of writing that just for my own scratch work. I would want to be careful to never write anything like that in terms of a justification on the AP exam. If I was trying to justify a limit in this way, I would have to write it out in that sentence form. That if I take the natural log of something getting infinitely larger without bound, then it does this. Okay? But for 20 homework problems, when I need to write 5 lines of work for each one of those, I'm perfectly fine with you writing the natural log of infinity with us having the understanding you're not saying that's a number, you're just using it as a symbol to abbreviate that concept of something getting infinitely larger without bound. Okay, so if I have the natural log of infinity, that would be like the log base e of infinity. If I rewrite that in its exponential form, I'm saying e to the what equals infinity. So if I'm saying that my answer has to get infinitely larger without bound, that exponent must be infinity. That 2.71828 would have to be raised to infinity in order to give me infinity. So my answer would be infinity. Another way to think about it is to think about what the graph of the natural log looks like. If I graph natural log x and I look at this as x is approaching infinity, what's my function doing? It's going off to infinity. So either way you want to look at that, you could say the limit as x approaches infinity of ln x would be infinity. All right? Then down here in the bottom, if I take something getting infinitely larger without bound and I subtract 1 from it, it's still going to get infinitely larger without bound. So again, I get an indeterminate form. I don't know what infinity divided by infinity is equal to. Is that 1? Is the numerator going to infinity faster than the denominator, so the overall thing is going to actually go to infinity? Is the denominator going to infinity a lot faster than the numerator, so the overall fraction is going to get smaller and go to 0? There's just no way to figure that out. That's what we mean by an indeterminate form. So here's what L'Hopital's rule says. If I have an indeterminate form in the form of 0 over 0 or some version of infinity over another version of infinity. What I mean by that is it can be positive infinity over positive infinity over negative infinity, negative infinity over positive infinity, negative infinity over negative infinity. Okay, so some version of infinity over the other. If I have either one of those scenarios, then L'Hopital's rule says the limit of that fraction will be equal to the limit of the derivative of its numerator over the derivative of its denominator. Now, we're not doing quotient rule here. We're not doing denominator times derivative numerator minus numerator times derivative denominator all over denominators. That's not what we're saying. We're literally just saying, take the function you have in the numerator, take its derivative. Take the function you have in the denominator, take its derivative. The limit of the original will be equal to the limit of the derivative divided by the derivative. Now, in terms of justification, we are very careful with our limit notation, that we constantly write our limit notation if we haven't taken the limit yet and that type of thing. So in terms of justification of how can I go from this step to this step and say they're equal, I'm going to put this capital H right here on top of my equal sign. And when I do that, that represents L'Hopital's. And that tells the reader the only way that this limit could be equal to this limit is by L'Hopital's rule. So I don't actually have to, every time I do one of these problems, come out to the side and write a paragraph justification that says, I've used L'Hopital's rule and what it does and what it is. Okay? That little H covers it. So let's go back to this example that we had up here a moment ago, where we had the limit as x approaches 1 and we had gotten 0 over 0. That's one of our indeterminate forms. So I'm going to use L'Hopital's rule. So I'm going to put the capital H right there on my equal sign to show what I'm doing. And I'm going to come over here and say the derivative of ln x is 1 over x. And the derivative of x minus 1 is going to be 1 minus 0, so it's going to be 1. Now, what I have is well behaved. I can use direct substitution. So I can go through and put 1 in the place of x, and I'll get 1 over 1, which is 1, and that's my limit. So in the beginning, I had gotten 0 in the denominator, which is undefined. And earlier in the year, we would have tried to find some type of algebraic way to rewrite that to make it well behaved to determine that limit. Now we have another tool at our disposal. I can only use L'Hopital's, though, when I have one of these indeterminate forms, or it will not give me the right answer. All right, look at another one. Example number 2. We've got the limit as x approaches infinity of e to the x over x squared. All right, so if I plug infinity in, if you take e, 2.718, keeps on going, if you take that and raise it to infinity, what are you going to get? Infinity, right. And if I have x squared, that means infinity times itself, something getting larger and larger without bound times something getting larger and larger without bound. What's that going to do? Infinity. Go to infinity. Going to get larger and larger without bound. So here's one of those indeterminate forms, infinity over infinity. So I'm going to put my h here to show my justification for what I'm about to do. What's the derivative of e to the x? E to the x. And what's the derivative of x squared? 2x. All right, so now I've made it well behaved. Now I'm good to go. And so I plug back in and I say, okay, e to infinity would be infinity, and 2 times infinity would be, man, well, I'm right back where I started from. That didn't do me any good. Actually, it did. I am making progress, because if you'll notice, I started with x to the second, and now I'm down to x to the first. What do I need to do? Just do it one more time, right? So I'm going to do L'Hopital's again. Now, watch carefully on this notation. Do you notice that up here there was only one h? I don't write h on top of every single equal sign all the way through my problem. I only write the h when I actually perform L'Hopital's. So if there is more than one h in your problem, that means you've done L'Hopital's more than one time. So if there are 2 h's, you did it twice. If there are 3 h's, you did it 3 times. So don't keep writing that h on your equal sign. You only write it when you actually perform L'Hopital's. So I'm going to, because this is still an indeterminate form, I have the right to use L'Hopital's, so I'm going to use it again. So derivative of e to the x would be, and the derivative of 2x would be, now I fixed my problem, right? Because I'm still going to get infinity in the numerator, but now I have a normal number in the denominator. If your numerator is getting infinitely larger without bound and you divide that by 2, it's still going to get infinitely larger without bound, right? It's just going to get there half as fast, but it'll still go there. All right, look at the next one. For the next one, we've got the limit as x approaches infinity of ln x. Now, we had that whole discussion up here a little bit ago about how that led us to infinity, and we had the drawings over here and all of that we discussed. Down here in the bottom, what is the cube root of infinity? Still infinity, right? Something getting infinitely larger without bound, you take the cube root of it, it's still going to get infinitely larger without bound, just a little slower. So I have my indeterminate form. So let's use L'Hopital's. So derivative of ln x is 1 over x. And derivative of x to the 1/3, because cube root of x is x to the 1/3, would be 1/3 x to the negative 2/3. Now, when we did limits before, we always made sure that we had what we were taking the limit of in its most simplified form before we started trying to plug numbers in. I want to do the same thing here. It's been a little while since we worked very much with limits, so this is great review for us to help us remember some of that stuff we learned earlier in the year. So I definitely want to simplify this down before I do anything else. This numerator up here is x to the negative 1. So when my bases are the same, I got x here and an x here. When my bases are the same and I'm dividing, I subtract my exponents, right? So I could say negative 1 minus a negative 2/3. That'd be negative 1 plus 2/3, right? So that would give me negative 1/3. So that's how we have this x to the 1/3 in the denominator. I also had 1 divided by 1/3, so that's how we have this 3 in the numerator. So I have not like taken a derivative here. There's no h there. I haven't done any kind of, crazy concoction. All I did was just simplify this fraction that I had down. And now I'm ready to then try and evaluate the limit again. All right, so when I go through and I plug in infinity, I've got 3 in the numerator, and I've got the cube root of infinity in the denominator. So what's my denominator? Infinity. If my numerator is staying the same, and my denominator is getting infinitely larger without bound, what is my overall fraction doing? Getting smaller, right. Does it ever switch to a negative number? No, because it's a positive divided by positive, right? So when we think getting smaller, sometimes we think negative infinity. It's not going to change to a negative value. It's a positive divided by positive. So what is that limit going to go to? 0, right? And that was something that we were very proficient with earlier in the year, so it's really good to start getting those principles back in our mind. When your numerator stays the same and your denominator gets infinitely larger without bound, the overall fraction is going to get smaller and smaller and smaller, so that limit will go to 0. We also use that, remember when we would go through to do a limit, we would divide everything by the highest power of x in the denominator, and our whole purpose in doing that was to get a number in the top and a variable in the bottom that would go to infinity, because a number divided by variable always went to 0. That's that same concept. All right, so look at example 4. Example 4 got really involved, and I didn't want you to be trying to copy back and forth and listen at the same time. So I filled this one in for you on your notes. So let's just go through this one together. All right, we start off over here with the limit as x approaches 0 of tan x minus x over x cubed. So if I plug 0 in, I've got the tangent of 0. All right, let's do a little bit of trig review here for a second. If I have tangent of 0, tangent is sine over cosine, right? So sine at 0 is 0, and cosine at 0 is 1, so that'd be 0 over 1, or 0. Okay. We're also, in just a minute, down here, we're going to hit the secant of 0, so let's go ahead and talk about that too. Secant is 1 over cosine, so if I had the secant at 0, that'd be 1 over the cosine at 0, so that's just going to give me 1. So we'll be filling those in the problem, but I just wanted to catch those to make sure that we remembered where those values were coming from. Okay, so right here, if we plug 0 in, we're going to get tangent of 0, which, as we just said, was 0 over 1, minus 0, and then down here in the bottom, 0 cubed. So that gives us 0 over 0, which is one of our indeterminate forms. So we're going to use L'Hopital's, right? So we can go through and put our capital H symbol showing we used L'Hopital's. And so I'm going to say the derivative of tangent is secant squared. The derivative of negative x is negative 1, and the derivative of x cubed is 3x squared. All right, so now let's plug in and see if we fixed it and made it well behaved. So we go through and we put in 0. We talked a moment ago about how the secant of 0 would be 1. So this is secant squared, so that's going to be 1 squared, minus 1, and then down here 3 times 0 squared. So again, I get 0 over 0. So as we saw earlier in the examples, sometimes we have to use L'Hopital's more than once. So I'm going to go through and I'm going to use L'Hopital's a second time. So the derivative of secant squared. All right, let's talk about that for a second. We've got that 2 written in the middle here, but remember, you could also write that as secant x in parentheses with a 2 on the outside, right? So if I use power rule for that, I'm going to get 2 times secant x in parentheses to the first, right? So that's what we've got right here, 2 times secant x to the first. Then I also have to multiply with chain rule. I have to multiply by the derivative of the inside, right? So if secant was on the inside, the derivative of secant is secant tangent. All right, so look at that one more time. We had secant squared x. So that's secant x to the second. So that would be 2 secant to the first times the derivative of secant. All right, and then the derivative of -1 is 0. In the bottom, derivative of 3x squared is 6x. All right, so now we plug in again. And again, we've already said secant of 0 is 1. So we plug in and we get 2 times 1 times 1 times, we've already said tangent is 0 over 1. So 2 times 1 times 1 times 0 over 1 is going to give me 0 in the top. And then down here, 6 times 0 in the bottom. Really? I still have an indeterminate form after all of this? I mean, like, isn't this getting worse instead of better? I mean, look at my numerator. I started off with something simple, and now I've got this monstrosity. Yeah, my numerator is getting worse, but look at my denominator. My denominator started out as a cube, then it was down to a square, now it's down to just x. If I will just do this one more time, I'll have a plain constant in the denominator, and I'll resolve my issue, right? Okay, so I need to take the derivative of 2 secant times secant is secant squared tangent. I'm going to come off to the side and work that as an entirely separate problem because that is an issue all to itself. So I'm going to come over here and say, okay, if I had y was equal to 2 secant squared tangent, because that was my numerator right here, 2 secant squared tangent. If I had y was 2 secant squared tangent, what would my derivative be? So I'm going to go through and I'm going to say I have a product, so I'm going to do first times derivative of second plus second times derivative of first. All right, so here's first, 2 secant squared, times derivative of second. Derivative of tangent is secant squared. So first times derivative of second, plus second, and now we need to go back and take the derivative of the first. So up here, I had 2 secant squared. Okay, so I'm going to do 2 times 2 is 4 secant to the first. So 4 secant to the first. And then I need to multiply by the derivative of the inside for chain rule, right? I need to do the derivative of secant, which is secant tangent. Look at that whole thing one more time. It's a product. So I'm going to do first times derivative of second. Derivative of tangent is secant squared. Plus second times derivative of first. The first was 2 secant squared, so I'm going to do chain rule. Outside would be 2 times 2 is 4 secant to the first, and then the derivative of secant is secant tangent. Okay, so let's simplify what we've got. We have 2 secant squared times secant squared, so that's 2 secant to the fourth. And then we have tangent times 4 secant times tangent. So secant times secant is secant squared, and tangent times tangent is tangent squared. So we get 2 secant to the fourth x plus 4 secant squared x times tangent squared. Again, that's a whole problem on its own. So that's why we went off to the side to figure it out. And now we can just take that and slot it in as our new numerator. Okay? Then, of course, the derivative, as we already mentioned, the derivative of that 6x is just going to give us 6. Now, when I do direct substitution, as I go through in my numerator, the secant at 0 is 1, the secant at 0 is 1, the tangent at 0 is 0. So now I'm going to have 2 times 1, so 2, plus 4 times 1 times 0, so 0. So 2 plus 0 gives me 2, and in the denominator I have 6. So now I'm actually able to come up with a limit. All right, look at example 5. For example number 5, we've got the limit as x approaches pi from the left. All right, let's do L'Hopital. So the derivative of sine is cosine, and the derivative of 1 minus cosine would be
negative sign, or sine.
Would be sine, right, because it'd be 1 minus the negative sign, so it would be sine. All right, so if I plug in pi up here, cosine at pi gives me cosine at pi? Negative 1, right. And if I do the sine at pi, that's 0. But because I was approaching pi from the left-hand side, those are going to be values that are getting smaller and smaller and smaller and smaller. So as I'm getting closer and closer to 0, my numerator is staying the same. My denominator is getting smaller and smaller and smaller. So what's the overall fraction doing? Getting bigger and bigger and bigger. So it's going to infinity. This was a positive value, but down here, all of these values as we're approaching pi from the left are going to give me negatives, so positive divided by negative is going to give me a negative. I get a negative infinity. Look in the back of the book, and that is not what it says. That is not the answer to that problem. Why? When is the only time that I can use L'Hopital's?
If it's indefinite.
If it is one of those indeterminate forms. But what will happen is I'll just get into the habit. I'm doing 20 of these for homework. I get into the habit. I'm going through, and the first thing I automatically do is take the derivative of the numerator and the derivative of the denominator. I do not have the right to do L'Hopital's if it is not 0 over 0 or an infinity over an infinity. It will literally give me the wrong answer if I use L'Hopital's when I'm not supposed to. And that's what they cautioned me about in example 5. If you go back to this problem's well behaved. I never needed to do L'Hopital's because if I go through and I just plug pi in, the sine at pi is 0 and the cosine at pi is -1, so I get 0 divided by 2, which is 0. So again, the key here is notice that if I used L'Hopital's when I was not supposed to, it will give me the wrong answer. Okay? So I want to be careful of that.